Now, as I mentioned before, right, we can think about sort of central metabolism or metabolism in any living organism as this pairing of both breakdown pathways or catabolic pathways and synthetic or anabolic pathways, right? And as I pointed out, we're mostly going to just have time to focus on the catabolic process. We're going to pick one really sort of main central one. We're going to really sort of dig into it because one of the main things I want to try and get you guys thinking about is some of the chemical logic that's involved in running this particular set of pathways. Because in many cases, what we're going to see is that a lot of that chemistry is shared for both anabolic and catabolic events. It's used maybe in slightly different ways, but a lot of the core chemistry is really very similar. And there's a fundamental logic that underpins a lot of what's going on that once you start to get it, you can sort of reason your way through how these pathways are going to go if you kind of have an idea of the beginning point and maybe a middle point and an end point, right? Okay, but let's, turning back to this idea of catabolic breakdown, right? Where again, the point here is to extract energy, right? That's what this is all really about. Well, and as you'll see, also molecules we need for making things, right? But in the process of doing this, for the purposes of getting energy, the main thing we're after here really is this flow of high potential electrons, right? Electrons with enough potential energy in them when they're yanked out of a molecule that has high potential energy, you can then turn around and do stuff with them, right? And that's just an example of what we're talking about here. I'm going to show you sort of a progressive extraction of some electrons from an ideal molecule. This is not one that ever would be used, to my knowledge, in any biological organism, but it illustrates a basic point. And the idea here is we're going to get these high potential electrons, both in the example I'm going to show you, as well as when we really do this in metabolism, in a series of oxidations, right? That's really what the catabolic pathways we're going to be talking about is a series of oxidation reactions that are designed to get at these high potential electrons and put them in places where we can actually use them, right? So this simple example of how this kind of thing would go, you imagine, well, let's say we got a molecule over here that has the highest potential energy in terms of its chemical structure, single carbon, which of course would be methane, right? So this is the highest energy compound. It's the most reduced carbon, right? For a simple carbon we can come up with. And methane has a free energy. If you think about the free energy of hydrolysis, the free energy of oxidizing for each of these steps I'm going to talk about. So if you took methane and you sort of fully combusted it all the way, the total amount of energy you have available if you totally combusted it all the way to CO2 is in the range of 820 kilojoules per mole. Let's just do that over here, kilojoules per mole, right? So that's a pretty decent amount of energy, right? But remember, we're going to do a series, right? Or I should say, we're going to do this stepwise. We're going to take those little steps I mentioned a couple of videos ago, steps, little incremental steps that make this principle happen. What's the next step we take, right? We do the first possible oxidation of methane, pull some electrons out of that. And of course, we would generate then an alcohol group here, which is of course methanol. And the combustion-free energy of methanol is about 703 kilojoules per mole, which means that first set of electrons we just popped off there, in principle, are worth somewhere in the range of 200 kilojoules per mole. It's pretty good, right? That's pretty good. So now, what's next? We can take the next step, do the next oxidation step, yank some more electrons out of this guy, turn that alcohol into an aldehyde, right, of course, which is, of course, from formaldehyde. Oops. And formaldehyde has a combustion-free energy of about minus 523 kilojoules per mole, right? So that next set of electrons, that was worth not quite another 200 kilojoules per mole, right? That's pretty good. We're stepping it down one bit at a time instead of blowing that whole methane up by combusting it all the way and losing that all this heat. We're sucking out of this electrons that have somewhere in the range of 180 to 200 kilojoules per mole of potential energy that would be usable, right? So I can keep going, do another one. Next step, turn that aldehyde, of course, into a carboxylic acid. My space here. All right, which is, of course, formic acid. Again, combustion-free energy. This guy is minus 285 kilojoules per mole, right? So that next set of electrons, again, you know, a couple hundred kilojoules per mole, pretty dang good. And at this point, we're just about done. Suck out a little more electrons, turn this guy all the way into carbon dioxide. We fully oxidized that carbon now. And in the process, pulled all these electrons out of this molecule. We're now down to 0 here because we can't oxidize that carbon any further. And that last set of electrons would then be worth, again, another couple hundred kilojoules per mole. So this is the kind of idea, there's a big picture that central catabolism is going to be doing. It's going to be taking a molecule, again, not methane, the same idea of highly reduced carbon, like methane over here, and then stepwise sucking electrons out of those bonds that are still worth some significant potential, or that are worth some significant potential energy, and then using those to go do stuff, right? Okay, that's the basic plan. Now, sort of switching, I guess, to something that is a real set of reactions, is what this is really going to look like. Go back to that scheme I showed you guys before, right? We have catabolism and anabolism. We're going to basically come down this way from these large polymers of molecules we can break down, like nucleic acids, polysaccharides, lipids, right? Breaking them down in a set of incremental steps that are going to generate those electrons, like we were just talking about, and energy. And basically, that's our energy currency, and those high potential electrons that we can then use to make things like ATP, where we can store it, right, in this unstable, thermodynamically unstable, but kinetically stable state that we can then pop the spring whenever we feel like it, we need it, right? Okay, a little bit more detail. Hopefully you've seen diagrams like this before. Here's that same basic diagram, but now blown up in a little bit higher level of detail. And we're going to spend most of our time, the rest of the class, just coming right down the central trunk of intermediary metabolism. And we're mostly going to focus on how energy is extracted from polysaccharides, right? Of course, that's one of the primary fuels that goes into this particular metabolic engine. And we're going to go through the steps of glycolysis down through TCA cycle and finally to the ultimate sort of little synthetic machine that's going to make our ATP from all these high potential electrons that come flowing out of this process. There are, of course, other ways to feed this central trunk. You can feed it from proteins, you can feed it from nucleic acids, from lipids. Many of these things either come in to the side or they can be converted into monosaccharides at the top and then run down through the process. So this is what we're going to be talking about for the rest of the course. But there are some big picture things that I want you guys to take away from this that are going to hopefully help sort of keep you grounded in sort of the big picture. So in the next video, we're going to start talking about that.